Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be going over problems 29 to 33 of the Geometry January 2015 Regents exam. Okay, these are the free response questions. All right, let's take a look at that problem 29. It says, given BE and AD intersect at point C, those two segments illustrated in these two triangles on the right. Segment BC is congruent to segment EC. Segment AC is congruent to DC. Segment AB and DE are drawn. So the task is to prove that triangle ABC is congruent to triangle DEC. One thing you want to note for this problem, problems involving proving that two triangles are congruent, is that SSS, SAS, ASA, AAS, or SAA postulates or the HL theorem can be used to prove that two triangles are congruent. Okay, so these are the steps we're going to use for this problem. First of all, we're going to label the triangles and determine which postulates or theorem we're going to use. All right, basically creating a plan for our proof using this information and the triangle that we have. Number two, we're going to write the proof. I'm going to use a two-column proof. Of course, you can use a paragraph proof if you want, or flowcharts proof. I'm going to use two-column proof because that's the format I like. So we're going to write a proof using what is given and can be deduced using the theorems in algebra and postulates. Then we're going to, along with part one, we're going to arrive at a conclusion. All right. Okay. So first things first, let's take a look at this triangle we have here and basically mark it up, annotate it using the information provided. All right, so first thing we know is that segment BC and EC are congruent. So segment BC is congruent to segment EC. Okay, so those two count as an S. S for two sides are congruent. Okay, now AC is congruent to DC. So let's go ahead and mark that on our triangle. AC is congruent to DC. That's another what? That's another side, a pair of sides that are congruent that counts as S. Now that's all the information we are given. Now, what else can we deduce from these two triangles? Now let me go ahead and give you a hint. What do you know about this angle, angle BCA, and this angle, angle ECD? These two angles are congruent because they are vertical angles. Okay, so congruent angles count as A's, congruent sides count as S. So what do we have here? SAS. Can two triangles be proven to be congruent using SAS? Absolutely. Look at that. SAS is one of the postulates that can be used to prove that two triangles are congruent. Okay? All right, so that's what we're going to be doing. We're going to set up our proof using the SAS format. I want to use SAS to conclude that our triangles are congruent. Okay? All right, so I'm going to go ahead and start my two-column proof. On the left column, I'm going to have my statements. And then on the right-hand column, I'm going to have my reasons. Okay, you have to have justification for why you're making whatever statement you're making. All right, statement number one, BC is congruent to EC. How do we know that? That information was given. And then next we have AC, segment AC is congruent to segment DC. How do we know that? That information is given also. So we have our S's in SAS. Now we have to talk about this angle that we graphed here. Let me scroll down a little bit so you can see all the vertices that construct that angle. So angle BCA is congruent to let me fix that a second. to ECD, right? So angle BCA is congruent to angle ECD. Why is that? Because they're vertical angles, okay? What do we know about vertical angles? Vertical angles are congruent. Okay, so we have our SAS. So what can we say? We can say that this is our conclusion. Triangle ABC is congruent to triangle DEC by the SAS congruency postulate. All right. Remember for SAS, the angle, so we have the two sides and then we have an angle that's corresponding. The angle has to basically be included between the two sides. All right, let's take a look at problem number 30. It reads, using a compass and a straight edge, construct the perpendicular bisector of side AR in triangle ART shown below. Leave all construction marks. Okay? Now, one thing you want to note is that when you draw an arc from a point, that arc is the locus of points that are equidistant from that point. Okay, so if you draw the complete circle, so that's the locus of points that are equidistant from that point. And if you just draw an arc, all the points in that arc are equidistant from the points that you started drawing your arc from using your compass. Okay, all right, so let's go ahead and take a look at the steps we're going to use to solve this problem. So first thing we're going to do is we're going to draw an arc from the 2 points above. We're going to draw an arc above and below in such a way that the arc basically overlaps or covers the region where we suspect the midpoint of the segment is located. All right, we'll draw one arc on the top and the bottom from both points. And then we want to draw them in such a way that both arcs intersect. All right, and then after that we'll draw a line through the points of intersection of the arcs above and below the segment we're creating the perpendicular bisector of. Okay, all right, so let's go ahead and do it. Now please bear with me. I'm using a virtual tool here. I'm not really familiar with it yet, so just bear with the whole process. It's much easier using an actual compass. All right, so let's say this is the triangle. We're bisecting side AR of the triangle. Okay, so what we're going to do, you basically put the tip of your compass on one point, and you want to extend the tip of your pencil to the other point. Okay, so the span of this compass is the length of AR. Okay, so that's basically how you set it up. Now, what we're going to do next is we're going to create an arc in such a way that it overlaps the area we feel that the perpendicular bisector is going to be. All right, so if you want to visualize, you can visualize that. Imagine that the point of the perpendicular bisector will be somewhere here. Okay, so our goal is to make sure the arc covers that area sufficiently. All right, so let's go ahead and draw the arc. So I'm just going to move it up here. Somewhere here we have the perpendicular bisector. So I'm just going to go ahead and make an arc like that above the segment, and then I am going to make another arc on the bottom. Okay, let's go ahead and do that. So make another arc here. Now what I'm going to do next is I'm going to I'll switch places. Okay, put the pointy tip of the compass on the other point, and then we're going to create another set of arcs in such a way that they intersect these two arcs that we have over here. Please do not, when you're making this adjustment, do not alter the width of your compass. Okay, So switch that around. Now using the same length, notice I didn't alter how wide my compass is, okay? And I'm just going to make another arc in such a way that they intersect these two arcs. So let's just scroll up. And then that goes the first arc. And then go down there and draw the second arc. Okay? All right, so that's what we're done. We're done with the compass now. Now what you're going to do next is just take your straight edge, and then you're going to connect the points of intersection of these two arcs, okay? These four arcs. So go from this point, just put your straight edge there, and draw a line right to this point right here. Shift it to the right a little bit, so it's perfect. So with your straight edge, you shouldn't have a problem with this. So that right there is your point of intersection. So your point of intersection is right there. This device is not working with me. Anyway, okay, so here, that goes the perpendicular bisector. All right. Now, I'm just going to go ahead and label it a little bit so you can understand what's going on here. So let's call this A, segment AD. Okay, so since this is a perpendicular bisector, what does that mean? It means that at the point of intersection, it bisects AR into two congruent halves. So this side is congruent to this side, and this angle is what? 90 degrees. Okay, so based on this construction, segment AD is the perpendicular bisector, perpendicular bisector of segment AR. All right, so that's basically how you bisect segments using your compass and straight edge. All right, let's take a look at problem 31. It says determine and state the measure in degrees of an interior angle of a regular decagon. Okay, so a few things to note. You want to know that if a polygon has n sides, the sum of angles, the sum of all interior angles is given by the formula 180 times the number of sides minus 2. All right, and if the polygon is regular, like in this case, each angle can be found by dividing the total number of the sum of all the interior angles by the total number of angles that there are. Okay, now these are the steps we're going to use to solve the problem. We're going to write down the formula first, the formula for finding the sum of all the interior angles of a triangle. Actually, to be ideally, we should use the second formula because we're going to be dividing it. But I'm going to break it up into two parts, okay? And then we're going to find n and substitute it into the equation, and then we will solve. All right? Let's go ahead and get started. Step number 1. Let's write down what the formula is. So the formula for the sum of interior angles of a triangle, so sum of interior angles of a polygon. It's not triangle, okay? Sorry about that. A polygon is given by 180 degrees times n minus 2. All right. Now, that's the formula for the sum of all the interior angles. Step 2, let's find out what n is, okay? That's all we need to know to find the sum of interior angles. So n is what? This problem tells us that it's a regular decagon. Now, what does decagon mean? If you think about decade, how many years is that? Decade is 10 years, right? So decagon is like a decade. It's a polygon with 10 sides. What does regular mean? Regular means that all the 10 sides are congruent. Since all the 10 sides are congruent, guess what? All the 10 angles are congruent also. All right? Okay, so we have an equiangular and equilateral decagon, polygon here. All right, so since decagon means 10 sides, n is going to be 10. So let's find the measure of all the angles, and then we're going to find the measure of one angle. Okay? So measure of all 10. I could have gone directly to the final formula, but there's something I want to highlight here. That's why I'm doing it this way. So you're going to go 180 times 2. I'm sorry, n is 10. 180 times 10 minus 2. 10 minus 2. If you compute that, we're going to have 180 times 8, which is equal to 1,440 degrees. Now, this is a big mistake most students make. They fail to read the question properly. Okay? The problem asks for an interior angle, just one of them. So most students will simply use n equals 10 in this formula. They get 1,440 and they think they are done. Okay, that's a big mistake a lot of students make. So please read the questions carefully so you can find exactly what you're being asked to find. So we're looking for one angle. All right, so this is the sum of 10 angles. So to get one angle, we have to divide this by n as indicated here. Okay, so we are not done yet. We have one more step. Measure of an angle is simply going to be 1440 divided by 10, okay, which is 144 degrees. That's the measure of each angle of a regular decagon. All right, let's take a look at problem number 32. It reads, write an equation of a line that is parallel to the line whose equation is 3y equals x plus 6 and that passes through the point negative 3, 4. Now, one thing you want to note is that in order for the coefficient of x to be the slope of the line, the equation of the line must be in slope-intercept form first, okay? So don't be in a haste to extract, to determine the slope without considering what form the equation is. So for example, in this problem, 3y equals x plus 6, this is not standard, it's not general, it's not slope-intercept form. So in order to determine the slope, you can't just say, oh, the slope is 1 because the coefficient of x is 1 here. That's inaccurate. You have to make sure that it's in slope-intercept form first before you determine the value of the slope. Okay, so these are the steps we're going to use to solve this problem. We're going to write down the point-slope form of the equation of a line. It's basically our map. It's going to guide us, tell us what we need and where we're going to put them. And then we're going to find the values of x1, y1, and m. Everything else is fixed in the point-slope form of the equation of the line. We're going to substitute them into the equation and then basically write it in slope-intercept form, namely isolate y. Okay, so let's start with the first step. The point-slope form of the equation of a line is y minus y1 equals mx minus x1. Okay, so we need to find y1, m, and x1. We have the point, negative 3, 4. Guess what? That's our x1, y1. Okay, so x1, y1 is the same thing as the point that the line goes through. So this follows that x1 is negative 3 and y1 is 4. Now how about m? Well, we don't know what m is yet. Let's find it. The equation can help us determine what m is, okay? So m is the coefficient of x when the equation is in slope-intercept form. What on earth is the slope-intercept form? The slope-intercept form is the y equals mx plus b form, the form you have when y is isolated, okay? So our task now is to get y isolated here. That can be achieved in just one step. Divide every single term by 3. That will result in the isolation of y, which is the slope-intercept form. So we have y equals 1/3 x plus 2. Now, what is the coefficient of x here? The coefficient of x is 1/2. Okay, so remember y equals mx plus b. m is the slope. All right, so now we know what m is. M is equal to positive 1/3. So we have m, we have x1, we have y1. What are we going to do next? We're just going to plug it into the point slope form of the equation of a line. So let me rewrite it. I always like to write my formulas down so that I don't make mistakes when substituting. Okay, so y minus y1, which is 4, equals m, which is 1/3, times x minus x1, which is negative 3. Now you have to be really careful here. This negative has nothing to do with that. So you have to keep that negative with the 3 and bring it in together. Okay, so let's simplify this. Put this in slope-intercept form. So we have y minus 4 equals, now we're going to distribute the 1/3, but before we do that, let's do one step at a time so no one gets confused. We have x minus times minus is plus, slash and dash. And then you can write x over 1 as a fraction and 3 over 1 as a fraction also. Now we're going to distribute 1/3 to these two terms in the parentheses. That yields y minus 4 equals 1/3 x plus 3 over 3. 3 over 3 is just 1, right? Okay, so to finish this off, we'll add 4 to both sides of the equation. So we're going to have y equals 1/3 x plus 3 over 3 is 1, right? So this is 1, so 1 plus 4 is 5. There goes the equation of a line that's parallel to the given line and goes through point -3, 4. Now, one point I failed to highlight, I should have stated that earlier, is that let's say this is L2, okay? So this one right here, let's say this is L2. And the original line, the original problem was L1. So let's put that right here. L1 is the original problem, 3y equals x plus 6. If two lines are parallel, what do we know? If L1 is parallel to L2 as indicated in this problem, then the slope of L1 will be equal to the slope of L2. They have the same slope, okay? So that is why I was able to use m equals 1/3 as the slope of the second line, because they are what? Parallel. Okay, so I forgot to state that earlier, but just keep that in mind. If they're parallel, you use exactly the same slope. If they're perpendicular, then you do the negative reciprocal of the slope of the first line to get the slope of the second line. All right, so our answer is y equals 1/3 x plus 5. All right, let's take a look at the last problem in this installment. It says in the diagram below, secants PQR, this secant right here, and PST are drawn to a circle from P, okay, from point P. If PR is 24 and PQ is 6 and PS is 8, determine and state the length of PT. Okay? All right, so let's see. One thing you want to note is that when you have a segment, if a segment cuts a circle at 2 points, it's known as a secant. Okay, so that's why these two segments are called secants, because they cut the circle at 2 points. The steps we're going to use in this problem, we'll start off by writing down an equation known as the secant-secant rule. Okay, is a secant theorem for circles and secants. Well, we're going to write that rule down, and then part 2, we're going to populate the different parts of that rule with the parts that we know and the parts that are unknown. And then we'll use our equation to find the unknown part. All right, so step 1, let's write down the secant-secant rule. Well, the secant-secant rule is not that complicated. We have two secants here. Notice that this portion right here, this is, I'm going to call this the external part. Okay, this is the external part of secant PR. All right, and secant PT also has an external part. Okay, let me be more specific here. So this section right here, this entire segment, that's the external part. Okay? And for the second one, for secant PT, this segment PS is the external part. All we need to know is the entire length and the external part, and we can set up our equation. Okay? The formula is not dependent on the internal part, at least not for this problem. Okay, so external part of secant PT. All right, so now we are ready to write down the secant rule. I'm going to write it in word form first, and then I'll apply it to this situation we have right here. Okay, so it's as follows. It's the whole secant, uh, for the first secant times the external part multiplied by, I'm sorry, if you multiply both of them together, you get the whole secant of the second secant times the external part. Okay, so this is a secant rule that can help you set up an equation to find parts of secants intersecting at a common point. All right, so this is a secant rule. We're going to use it to set up an equation. Now, let's apply this formula to this scenario that we're working on right here. So the whole secant for the first one is PR, so it's PR multiplied by the external part. The external part is PQ. All right, so that's the product for secant 1. For secant 2, the same story. The whole secant is PT multiplied by the external part, which is PS. Okay, excellent. So this is the equation that we want to deal with. Now, for step 2, we're just going to populate this equation with the measures we know and find the one that we do not know. Okay? All right, so PR is 24, PQ is 6, PT is what? That's what we do not know. Okay? And then PS is 8 units. All right, so we have this algebraic equation here. All we just have to do is solve for PT. Okay, so we can multiply and divide, but I'll be lazy. I'll divide first. Okay, so divide by 8 because I want to reduce before I multiply so I can save time. So this 8's cancel out. So the length of secant PT is equal to, now let's see what we can do here. 8 goes here once, 8 goes here 3 times, 3 times 6 is 18. So that is the length of PT. Okay, so let's go ahead and state that. The length of PT secant PT is 18 units. All right, so that's that. Thanks so much for taking the time to watch this presentation. We really appreciate it. We'd like your feedback. If you found this presentation beneficial, do give us a thumbs up. We'll appreciate it. Do not forget to subscribe to our channel so you can get instant updates to other great math tutorials such as this and also the remainder of this review installment. If you have any questions or like support getting ready for your geometry Regents, please place a comment in the comment section below and we'll be glad to address it as soon as possible. More clips can be found on mathgotserved.com under test prep. Thanks again for watching and have a wonderful day.